Good afternoon, good morning, or late good evening, wherever you are. This is the International Space Science Institute in Bern, in Switzerland, with its Game Changers online seminar. And in that series here, we are talking about cosmology. I'm filling in for Maurizio Falanga. So today we're talking about the missing baryons in the universe. And I, as a planetary scientist, wasn't aware that, as I read in the abstract here, that baryons are rare in stars, which I wouldn't have expected. But anyways, we have Professor Wei Cui from the Department of Astronomy of the Tsinghua University in China to explain us, about where the missing baryons all are. And Professor Cui, has spent a lot of his career in the United States. He graduated in physics from the University of Wisconsin-Madison, and then joined for some time MIT, moved on to Purdue University, and worked for the RXTE satellite and the Veritas mission. Interestingly enough, there's a Veritas mission going to Venus sometime soon. So some names are used very often. And in 2016, he accepted to become a professor at the University of Tsinghua, where he joined the physics department and later the Department of Astronomy. He's the PI of the proposed Hot Universe Baryon Surveyor mission, which aims at filling the void in probing cosmic baryons. So he's the expert in explaining us where all those baryons are. So Professor Wei Cui, it's midnight for you, as I understand. So thank you very much for staying up and giving us this seminar, and the floor is all yours. Oh, let me say at the outset that, for many of you, know that already, but for asking questions, you have two ways. You can write your question in the chat, and we will go through those questions in the chat after the seminar, or you can raise your hand using the feature on Zoom, in which case you will be given the floor to ask your question in person. And with that, I hand over to you, and looking forward to your seminar. Thank you.
Thank you very much, Tillman. It is really a pleasure to share the story with your audience here. And so I picked my title, Where Are All the Baryons in the Universe? I guess this is a question dates back to really for people working on cosmology. These are the fundamental questions, I guess, raised to that artistically to these very fundamental questions. Regarding, our human being, and so where the life, how the life starts, and growing and aging, facing inevitable death, and then can think about the afterlife, perhaps. I think this is a kind of fundamental questions as astronomers or cosmologists like to think about if we, look at in the context of the universe. And so if I rephrase these questions, where does the universe come from? I guess this is a question that many people, smart people, are working on. I actually browsed some of the previous seminars, and they are excellent talks. I guess it's fair to say we still do not know. And we do not even know whether, frankly, there is a beginning. But the modern cosmology, I guess the foundation is this Big Bang theory. And once the universe started in a highly dense and really very hot state, then expand and cools subsequently. This is a very successful theory, and because some of the key predictions are verified observationally, I list these very key predictions: the Hubble's observation of the expansion of the universe, and the nuclear synthesis, and not all elements we know of are necessarily producing stars. and some may be the primordial the elements produced during the early phase of the universe. In fact, of course, the prediction of the existence of cosmic wave background, which now is becoming a fantastic laboratory for physicists and astronomers alike, and led to a number of Nobel Prizes, and probably there will be more, I would be, guessing. So, but once the universe started, and through observations, we know more and more. We've learned awful a lot because thanks to really advancement in observations, the telescopes are getting more powerful. If you look at this diagram, this is fairly typical that the horizontal axis is time, cosmic time, and every section you can think of as a sort of a 2D analog of a 3D sort of 3D universe. And they are very important epochs. I've mentioned a few, the Big Bang nuclear synthesis, cosmic wave background. So this is really give us a tool to look into the universe very early on, seconds to minutes, and then gradually we start to see that light, first light in the universe, and then a darker period before first stars are born, and then the first starlight will reionize these neutral medium, and then first galaxies form and evolve. I think now the telescopes are powerful enough. We're looking back in time and start to probe really the early days of the universe. So we know now more and more that some of the fundamental properties of the universe early on. I'm gonna zoom on to a issue that observationally that we see as the galaxies evolve, the baryons seem to go missing. So I elaborate on this point. This is sort of the theme of my talk. I'll explain a little bit more. But before I can talk about the missing baryons, as Timon was introducing, I have to answer the question of how do we know how many baryons were produced in the universe, right? Before we can talk about the missing. So really that in the early epoch of the universe, you can see the time very early, right? Millisecond to minutes. When universe expands, when it becomes cool enough, initially all matter exists in the form of elementary particles, right? In terms of quarks and so on. They were not even protons or neutrons. So baryons are particles like protons and neutrons made of 3 quarks. And so when the universe expands, cool enough, quarks start to combine to give us baryons, protons and neutrons. And then when the condition is right, the protons and neutrons, just like inside stars, it's the core of stars, it can undergo fusion to produce heavier and heavier elements. So this is the general idea of the Big Bang nuclear synthesis. Early on, the universe that expanded to the temperature that's just right to form baryons, and then baryons then may fuse and give us heavier and heavier elements through processes that are very familiar to nuclear physicists. So these are very well understood. But it's a race against time. The universe keeps expanding, it getting cooler, and really a few minutes after the universe, the Big Bang, universe become too cold to sustain fusion. So the heaviest element really it can make is lithium. Okay, But not everything on this diagram is stable. For instance, the tritium decays to helium with a half-life of 12 years, and beryllium decays to lithium-7 with even shorter time, only 2 months or so half-life. So when all said and done, there are a few stable isotopes that are potentially observable. And this gives us opportunity to look into very early universe. So this is this diagram shows the theoretical calculations, like how much of each of these isotopes color-coded, helium-4, deuterium, helium-3, lithium-7. These curves are the theoretical calculations, how much of each isotope that was made during the Big Bang nucleosynthesis. And as you can see that it depends on critical parameter, which is how many baryons were produced, essentially. So this is uncertain, but the horizontal line shows the results of very difficult observations, measurements. The width of the line indicates the uncertainties in the measurements. So these were measured through very difficult observations. I don't have time to explain, but the point is that the intersection between observation and the theoretical calculation would give us how many baryons, the amount of baryons that were produced during the Big Bang nucleosynthesis. These are independent measurements, but it's remarkable. They all give the same answer. There is a little bit of problem with the lithium-7, as you can see. Many papers were written trying to explain, probably related to how difficult these measurements are, because when you see these isotopes, the question is, how do you know they were primordial versus, the stellar production? I guess this is perhaps contribute to these kind of discrepancies, but agreement is truly remarkable. It gives us, in terms of sort of energy density, so these are the baryons. Okay, so this is a scale, the Hubble constant, essentially. If you plug in the Hubble constant around the 0.7, 0.68 or so measured by Planck, for instance, that gives us the chart many of you probably have seen, the composition of the universe, the ordinary matter. This is the baryonic matter I'm talking about, only account for roughly 5% of the universe. But baryonic matter, unlike a dark matter, is visible matter. Through observing that baryonic matter, we learn about the dark component of the universe, which we have really no idea. We give them names, but we still do not know the nature of dark matter and the dark energy. Okay, so, but baryonic matter is a window for us to look into the universe, to learn about the entire universe. So, but the story I'm going to tell you is, even though it's a tiny fraction, 5%, but about half of it is missing, actually. So how do we know? Well, that we actually, before I tell you how we know the missing baryon issues, that there's another tool we can learn about the universe. This great laboratory, cosmic wave background. And I noticed that there was a talk on this topic. So this is great, saved me a lot of time. The point is that at a certain epoch, 400,000 years after the Big Bang, one that neutral atoms are formed, all of a sudden the free electrons are locked in to atoms. Okay, so before that happens, the light photons scatter off electrons, free electrons, so they're constrained. They are not freely sort of fill the whole universe, but once the electrons are depleted in some sense, that the light is free to fill the entire universe. So this is what's now known as the cosmic wave background, because the expansion of the universe, the wavelengths get stretched initially, they are much shorter wavelengths. Okay, so this is in terms of looking for electromagnetic signal. This is how far we can look back. This is a microwave background. Okay, this is a great book by one of one of the big names in this business, John Mather, and a very interesting story that if you have not read it, I recommend this book. So it was discovered by accident by two engineers in Bell Lab, that Penzias and Wilson. I think you may know the story. And then in the late 80s and early 90s, NASA's launched a satellite, COBE, that measures the cosmic wave background and give us this map. Very uniform, isotropic, right? You see all directions roughly the same, and to very high accuracy. Two big results come out of COBE is that if you look at the spectrum of this radiation, it's nearly a perfect blackbody. This is exactly how you would expect that the cosmic wave background. And if you subtract a constant off that very uniform looking map, and then you actually see fluctuations at the level of roughly 1 part in 100,000. And these are the fluctuations that are the cosmic seeds that eventually evolve and grow into the structures we see. So it's not perfectly uniform. They are these fluctuations that eventually evolve. And John Mather and George Smoot and won the Nobel Prize for the work, the COBE work. If you look at the distribution of cosmic seeds, essentially we use a power spectrum, almost like a Fourier transformation on spherical, that in spherical units. You look at the distribution and essentially the clustering of these seeds, and they are not totally randomly distributed. You see these peaks, now known as acoustic peaks, and this is not, I don't have time to really go into this, but the point is that these agrees with the theoretical expectations quite well. You see the green line. This is now the prevailing theory, right? The model and WCDM model, and you can see how well it can fit the data. I choose this data. There are much better versions of this kind of diagram, but respecting the history, and these were very difficult measurements early on, combination of balloons and satellites that covers wide range of spatial scales. This essentially represents the spatial scales from small to large scales. Okay, so how this clustering of these fluctuations. So in this model, there are many important parameters, including the Hubble constant and, of course, the baryonic, that energy density I was referring to. I'm not sure if you remember the last number, the results from looking at the isotopes, primordial isotopes, and that number was 0.0214. And from the cosmic wave background, you see this number, this is almost exactly the same. So in other words, 400,000 years after the Big Bang, all the baryons produced in the Big Bang nucleosynthesis are still there. We see all of them, okay? But as we move on, as the universe evolves, and now we can actually look at how many baryons or the distribution of baryons through optical observations. So roughly here is how it goes. You can look at a very bright background source like a quasar, very bright, using quasar light as tracers. As the light propagates towards us, it will go through many material clouds, if you wish. Gas will absorb light, And so what's shown in the bottom is now known as Lyman alpha forest. And this is actually one line, the Lyman alpha line, redshifted to the frame of the absorber. So it depends on where where it's produced, it's redshifted to different wavelengths. That's why you see this forest of absorption lines. Okay, so from this kind of data, you can actually do awful a lot. For instance, at each redshift, in other words, each sort of epoch, you can, through surveys, many different line of sights, and you can, in fact, get a census of baryons. And so long story short, what we found was that at a high redshift, looks like from observations, the baryons are probably all there. Of course, there is a sensitivity issue. It's impossible we can see 100%, right? So because the signal to noise issues, but looks like most, if not all, are there. But if you look at the local universe, and today, then through that kind of studies, we see only half of them. Now the question is really, where are the rest of the baryons? Okay, so this is on the universe as a whole on the cosmic scale. There is a related problem on galaxy scale, smaller scale. We see sort of missing baryon problem as well. So this diagram shows you put different systems on this diagram. The vertical axis is a baryon fraction. In other words, what is a fraction of baryonic matter in total matter, right? As I already mentioned, the matter in the universe is dominated by dark matter, in fact. Baryonic matter is only a small fraction, about 16, 17% shown in this dotted line here. That's the cosmic average. And the horizontal axis for all practical purposes, you can think of this as a mass of the system. So only the most massive systems like clusters, rich clusters, the baryon fraction is equal to the cosmic average. But if you look at the systems with lower and lower mass, then you see a lower and lower baryonic fraction. Here's the Milky Way here. When you go to dwarf galaxies, then you hardly see any baryons, actually. And that's why dwarf galaxies, for people interested in looking for dark matter signals, dwarf galaxies are great targets because you see the low baryonic, the baryon fraction there. So the matter is nearly all dark matter in these kind of systems. So again, the question is, what happened to the baryons in galaxy? So these are sort of the related issues. And we do not know the answer because that, as I later on will describe, due to observations, lack of data. But the theorists have give us a hint. Perhaps there's an answer to both, a solution to both questions. Through numerical simulations, the theorists found that they are baryons that are heated to very high temperatures, millions of degrees, very low density, to make them very hard to detect currently. There are no instruments that are sensitive enough, in soft X-ray to detect them. If this is true, if there are a lot of, for instance, baryons in the hot halos of galaxies, and that would explain the low baryon fraction in galaxies. In other words, they are hiding in halos we cannot see. And this is typically, right, how we do this, that you hide them. So they're missing, and though the answer is, well, at present, you don't have a way of seeing them. And similarly, there are a lot of these hot gas, according to these simulations, presenting the cosmic web. Okay, and we cannot see, perhaps this is the answer to the global missing baryon problem. And now the challenge for observers is to not only find these baryons, but to understand their properties. This is very important, as I will elaborate later on. So are there observational evidences and the theorists are on the right track? The answer is yes. In fact, so this middle panel shows a Chandra observations, X-ray observations of a Milky Way-like galaxy. You do see these hot halos, right? And so the Chandra soft band, you see extended halos above and below the disk. However, if this postage stamp fits globally into this is what sort of we understand, at least optically, what a galaxy looks like. But over the past 10, 15 years, there's a paradigm shift. Our view of galaxies, actually, that we realized that much of the galaxy we probably do not see. So this is now a diagram you probably see often, and galaxies are a lot more complicated. So there's gas, there's a lot of gas around these galaxies. Now the term is circumgalactic medium, and the cold phase that can be observed in long wavelengths, and indeed we've seen them. But the theorists told us the most extended phase of the medium is a hot gas, which we do not see presently. That extends much further than what this picture shows. This picture only shows this kind of scales. Okay, so and this is a great laboratory that invokes a lot of important physical processes, such as how the mass gets accreted from large scale structures onto galaxies to fuel star formation. And when stars evolve and die, and supernova or stellar wind may blow baryons out, in fact, heating them, may eject them to very, very far. And maybe that's how the missing baryons are produced. And so there is this baryon cycles here, and these baryons may cool, fall back again to fuel the formation of the next generation of stars. So this picture is our theoretical speculation, whether this is true or not, and we need further observations. In fact, the diffuse X-ray background, no matter which direction we look, we see this background radiation, almost like a cosmic wave, microwave background. In X-ray too, we see all directions there's X-ray emission, and a component of it looks like is from the hot halo of galaxy, our own galaxy. So these are sort of some of the evidence. Perhaps some of the hot baryons are indeed hidden in the halo of galaxies. And this is important because that, as I was explaining, this really is become a bottleneck in our understanding of the evolution of galaxies. Okay, because we do not understand, due to the lack of data, these very important processes nowadays known as feedback. The galaxies actively feedback, and produce and eject this gas and to the surroundings, and then causes these baryon cycles. Okay, this is problem. The importance of this problem is captured in the decadal survey of the United States, and this Astro 2020. You see 3 themes. One of the themes is cosmic ecosystems, and in it, a priority direction is indeed to understand the drivers of galaxy growth. Is this kind of a problem is exactly what I was describing. And in the US, there's a vision for the future, and that's clearly laid out. And this is the direction probably US will plan for the observing facilities. This is now the question is, can we see what can we do to actually observe these baryons to verify these theoretical pictures? This what's shown here are the baryons hidden in the cosmic web. This is from a numerical simulation. You see that these are million-degree gas. Because of low density and they emitting soft X-rays, it's a technical challenge, really. And one way of doing this is through high-resolution spectroscopy. Okay, and because that these gas should be rich in lines in their spectrum. So if we have high-resolution detectors, we might be able to enhance signal-to-noise ratio by various of techniques, such as narrow band imaging to increase signal-to-noise ratio. This is not foreign to astronomers, right? This is used at all wavelengths almost, actually beyond astronomy, in electronics too. So this is a general idea, and but it's very difficult. And because, for instance, our Milky Way, I was explaining, there is a hot gas in the Milky Way too. And if you want to look at the extragalactic signal, this is a foreground. This shows the spectrum of the foreground. You see rich in lines, almost all lines, in fact, the spectrum in nearly all lines. The power law continuum is because of background AGN, okay? And now the question is, how do we, if we look at the extragalactic target, how do we distinguish the lines from the foreground lines? And that's where we need a high resolution, okay? You need to be able to separate redshifted lines from the foreground. And for instance, if we zoom on to oxygen 7 and 8, and what's shown here is that I'm looking at the extragalactic target, a group in this particular case. The orange shows the signal we want to detect, and the blue are the foreground. So with different detector resolution, you can see that at a higher resolution, like 4 eV or so in soft X-ray, you start to see these lines and better, not only oxygen 8 and oxygen 7 as well. And if now you even 8 eV, and you hardly see oxygen 7. And what's the best we can do with the current non-dispersive spectrometer, like CCD? CCD give us on the order of 100 eV, very far from here. Although we can achieve high resolution with gratings, but for diffuse emissions, the gratings are, is not very useful. It's useless, in fact. For dispersive spectrometer, we cannot use gratings to look at these kind of diffuse emission everywhere. So as I was saying, with a high resolution detector, you can do narrowband imaging. And of course, once we have a spectrum, we can do all kinds of precise measurements, such as the standard plasma diagnostics to determine density, temperature, and abundance. Okay, so this is why we need a high resolution spectrum. So the very important elements is oxygen, and in this wavelength, it's most abundant and the lines are strongest. Okay, at about 0.6 keV or so. We can look at the direct emission through emission lines, or we can use almost like the Lyman alpha forest type of measurements. We use a background source, AGN, and use its light and through absorption lines to probe the hot medium. So both approaches are possible. And this is something we discussed quite a long time ago, and whether we can have a mission that to actually do some observations. And this is what I will describe to you, a mission called the HUBS, the Hard Universe Baryon Surveyor. So the HUBS concept is exactly optimized to do the kind of observations I was describing, and you would adopt a novel, really, technology. These are so-called microcalorimeters with a high resolution. In our design, we are considering both approaches, right? The main array with 2 eV resolution to detect a direct emission from, say, in this example, the halos, hot halos of a galaxy. Or we can look at background AGN through absorption line to probe this hot medium. So we actually adopt a hybrid design. So there's a central subarray. We can making them small, and we potentially can achieve even better resolution. So this is the idea, because for absorption line study, you observe a point source. So as long as you cover the point spare function, and you don't need to make the whole detector this resolution. Yeah, maybe you'll ask, why don't you make the whole array with this kind of resolution then? This is a technology limitation. We cannot, because these are cryogenic detectors. They have to operate at 50 millikelvin, for instance. So to read out these detector signals from these pixels is a technical challenge. You cannot have many wires for this kind of a very low detector experiment. We have to use a technique called multiplexing. You use a small number of wires to read out the entire array. And currently, the technology is limited. We can read out about thousands of pixels or so. And so that's why the total number of pixels currently, that we can read out with this kind of technique is limited. This is the reason why we cannot make the whole array, that with this kind of small pixels, okay? I'm gonna skip all the technical details that are not much. I'll briefly mention them, next slide. And the telescope, the requirement is modest, except we want a large field of view, because the target we look at is diffuse emission, the field of view. So the larger field of view, the more photons we let in, so the brighter the signal. Okay, so this is what we envisioned. And a few words on this kind of detector. So it's a very simple detector idea. It's a thermal detector, consists of 3 parts: absorber that absorbs the photons coming in, deposit energy, heat up the detector, raise the temperature delta T. If you have a sensitive thermometer to measure that delta T, if you know the heat capacity, C delta T give you basically the energy of the photon. So every photon produces a thermal pulse, right? When heat leaks out, the temperature recovers. So every photon gives us a pulse. So it's a single photon detector. We measure the energy of each photon through this pulse height. The pulse height will be proportional. So how accurately we can measure the pulse height essentially determines how accurately we can determine the energy, and that is our spectral resolution. So that's given by this formula. As you can see in this formula, the lower the temperature, the better the energy resolution, right? That's why it's a cryogenic detector, and we want to make them small. So C is small, and these are why it's microcalorimeter. And another thing that's important is the sensitivity of the thermometer. We typically adopt something that is resistance is sensitive to temperature. The higher the sensitivity, then the higher resolution in principle we can get. This has been developed for decades. And when I was a student and in Wisconsin, so we first started to develop this kind of detectors and construct a sounding rocket experiment to make sure these detectors work in space, because these low temperature detectors, not only a detector has to work, the refrigerator has to work, and many technologies. And this is a very successful. The Japanese adopted by for their Astro E satellite, Hitomi. Unfortunately, many of you may know 3 times due to human errors, it failed. Okay, so have nothing to do with the detector. It is the first time it failed to reach the orbit and reasons like this. Most recently, Hitomi, due to human error, totally disintegrated. So very unfortunate that the microcalorimeters have not reached its potential yet, but we already have get a taste of the potential. This is a few minutes of sounding rocket data of basic diffuse X-ray background, hot gas in our Milky Way. And the bottom is a theoretical prediction of the hot ISM. You see reaching lines. And without a fancy analysis, you can see the oxygen 7, oxygen 8, even a few minutes of data, you can see these lines very well, right? So this really shows a potential. And remarkably, this is the only high resolution X-ray spectrum, actually even today, because not for the lack of try, as I was describing, that many attempts fail, unfortunately. Before Hitomi disintegrated, through a semi-transparent window for calibration purposes, and in non-really observing mode, it observed the Perseus cluster produce this beautiful spectrum you can see. For comparison, that red dotted lines are what you would expect from a CCD. There's no way you see these lines. These are the sort of hydrogen-like, helium-like iron, very hot gas in cluster, even much hotter than the type of missing baryon temperature I was describing, okay? And so you see the most dominant iron lines. So this really gives us hope that this is probably, we are gonna start a new era of X-ray astronomy. Japanese are gonna try again next year, launch XRISM satellite, and with this kind of detectors. So we eventually need a detector to replace CCD so that we can do X, Y, and wavelengths mapping, okay? I can dream of a day we could do this in X-ray, okay? And of course, we will be dealing with highly ionized, hydrogen-like and helium-like ions that like oxygen and iron. This is, of course, that in Europe, Athena is going to be the next X-ray observatory, and both Hubs and Athena will adopt this kind of superconducting sensors and to achieve high resolution. So these, if we bias the detector in this transition range between normal and the superconducting state, you see its resistance is very sensitive to temperature. A little bit of change in temperature give a big change in resistance. So alpha will be very big. So that's why we're moving to superconducting microcalorimeters. And before, the thermometer is based on doped silicon. So those are semiconductor based. And with alpha, only a few, really. With this kind of sensor, we can achieve alpha, in fact, over 1,000. So this, in principle, we can expect a higher resolution, okay? And we can do a comparison of figure merit in terms of detect these lines, what, you know, how you would optimize, right? Given the energy of a line, given continuum, exposure time, and then it really signal to noise. It only depends on this product of resolution of spectrometer, effective area, field of view. So I would define this figure merit to compare different instruments. And as you can see in this table, Hubs is highly optimized to detect the missing baryons. Okay, this is a big number. So it's really a matter of a small field of view instrument versus Athena and versus large field of views. Okay, Athena will be great. No, really, it's ultimate machine to look at the high Z universe, smaller target, in other words. It doesn't depend on the field of view. But on the other hand, the Hubs is very powerful in detect these diffuse emission that fills the entire field of view because its field of view is so much bigger. Okay, So very complementary in science that core science goes. This is, and here is a preliminary design of the spacecraft that sort of a normal looking. There are some novel features. Actually, you cannot see the door that's hidden inside here. The telescope is here, optics, focus X-rays onto the detectors in this hole, essentially. And so that's how we're going to be proceeding. The key technologies, obviously, the number one is the detector, these microcalorimeter array. And this is an example of optimization. We did a lot of trade-off to achieve, see, we're going to cut off at 2 keV instead of the typical 10 keV for the X-ray telescopes. And again, for technical reasons, because it's easier for us to achieve high energy resolution. And of course, most of the lines are below 1 keV, in fact. So we're highly focused on scientific goals for hubs. And unlike Athena, we need a very large pixels. This is different to cover a large field of view. We need a pixels about 16 times the Athena pixels in area. This is, again, a technical challenge because remember, the larger the heat capacity, the worse the energy resolution. So we need a large pixels yet keep the heat capacity reasonable. So we have to make it very thin. That's also why we choose lower energy bound, because to increasing the detection efficiency, right? We can afford to use very thin absorbers. So basically, there's a lot of consideration, optimization, trade-off going on in this design. This is what I was talking about, and there's a limitation on how many pixels we can read out. This is a key technology, and of course, the refrigerator and optics. And key here is a large field of view. So once we have a mission like hubs, and besides our core science goals, there's a lot of other things we could do. There's a lot of line-rich sources like supernova remnants and active stars, and those are also line-rich, and also a lot of transients. We don't understand their origin, and much progress can probably be made to look at the spectrum, whether they are lines, because these sources, many of them are thought are powered by outflows from black holes. And we still do not know the composition of these jets, that if we can see lines like SS433, then we have some idea about the composition of these jets. So there are a lot of other goals, including, in fact, direct search for dark matter if they are light dark matter particles. Okay, and I'll almost end of my talk. And for those of you who are interested, we have a website here. You can learn more about the hubs, and we're actively organizing to do science planning, mock observations, selecting targets, and so on. And we communicate with the international communities on occasions. There are hubs workshop. In fact, we organized a focus meeting 2018 in Vienna at IAU General Assembly, and a lot of key people working on similar missions are gathered. We discuss the plans for these missing baryon type of missions, including some of the key people working on the Japanese missions and US links and so on. The status of hubs, and we've completed a conceptual study. We are now in roughly phase 1, I guess, in NASA terms. So we're developing technology, and we're hoping it goes as this. So 5 years of technology development to advance technology readiness levels, and then enter the construction phase, launch around 2030, and operation for at least 5 years. We're hoping for 8. That's how we're designing this, the mission. I like to say that we're intending to do a Pathfinder mission to test technology and on the China space station, which just almost completed actually. In fact, this week, the new experimental compartment just docked. So the gradually experiments will be the uploaded and conducted. So we're hoping to do a Pathfinder mission. Of course, not just technology demonstration. We intend to do all-sky survey and to look at with a collimated detector, no optics, because of the environment, we worry about contamination, and do a Rosette style or eRosetta style survey, and mostly focus on the Milky Way hot gas. And so last slide, I guess I don't have a way of really concluding. I guess let me just say, we are witnessing probably a new era of X-ray astronomy, and fingers crossed, and hopefully CRISM, the Japanese mission next year, will be successful. That will be really open a new era of high resolution X-ray spectroscopy, and we are talking about new era of technology, and with these new microcalorimeters, and I'm hoping eventually probably will replace CCD. It will take a while, and new era of X-ray spectroscopy, and hopefully that lead to the breakthrough science. Thank you very much.
Thank you very much for this excellent and fascinating talk about the missing baryons, and I sure hope you'll discover them. There's already a number of questions in the chat, but let me just remind people that there are two ways of posing questions to the speaker. One is, as some already did, write your question in the chat, in which case I will read them for the audience and the speaker. But you could also use the features of Zoom to raise your hand, and then Willie will hand over the floor to you. So let me begin with Pavel Krupa's question. That's earlier in the talk, and refers to the stuff that you presented relatively early on. And the question is, can the existing stars and the moderate star formation rate, a few megasuns per year, produce enough energy to blow gas out to 100 to 300 kiloparsec from within the deep potential well of the galaxy?
So this is related to this concept of feedback that's been studied very actively. So I guess without directly addressing this, I guess the question is related to through accretion, whether the energy produced will be enough to, this falls in a general category of the feedback scenario. And so through outflows in accreting systems. In fact, one of the important processes is accretion onto black holes that to produce jets, outflows, and perhaps these is a very important channel of feedback. Another channel is a stellar feedback through mostly the wind and the supernova explosion. It has to be energetic enough to eject heat and eject these hot gas to large distance, so that if the theorists are correct, these very hot gas distributed over large distance up to the very radius, even beyond around the galaxies, even into the intergalactic space, IGMs. So it needs to be indeed the accreting systems through accretion. Accretion powered outflows is an important channel.
Thank you, William, for correcting my misreading of M sun. It was, of course, the mass of the sun. Yeah. The next question is by Ludwig Klein. The presence of numerous missing baryons in halos would imply that there should be as many electrons. Aren't these electrons detectable by their radio emissions? Is there independent evidence that electrons are missing too?
It's a very interesting question and a very important one. In fact, there are direct observations. These are that through the perturbation on the microwave background, because of this hot gas, as the question implies, they are electrons too, and so the cosmic wave background photons can scatter off, and through these collisions, the spectrum of the cosmic wave background will be distorted. This is known as SZ effect. These are actually observed. So the missing baryon problems, I guess that right now, I put in quotes, actually there are more and more evidence. Actually, the theorists are probably correct. There are these hot gases, and through some of the indirect observations, like I was describing, these distortion of the cosmic wave background spectrum, and also FRBs. FRBs, you can use FRBs through in radio frequency. You can measure the dispersion, and you get at the amount of free electrons in space. Indeed, they can be observed through these, I guess indirect is a relative term, but to use different probes like FRBs or cosmic wave background.
Okay, so we have one raised hand, and I switch over to the Jeffrey Linsky's question, and then come back to the chat again. So Jeff, the floor is yours. Will he have you open the microphone for him? I think he has to open the microphone himself. You seem to be muted, Jeff.
Can you hear me, please?
Yes, now we can hear you.
The question I have is the following. Since low mass galaxies are baryon poor, and it's likely that the baryons in the galaxies are lost into halos by virtue of supernovae or stellar winds, my question is, why is the dark matter not also expelled from the galaxies?
You mean galaxies literally is you're just looking at the disk, or
Well,
is the cosmic, the whole ecosystem?
No,
the dark matter halos.
What I'm saying is optically, low mass galaxies are baryon poor.
Yes.
We don't see the extended halos. So why is it that, so the baryons are presumably expelled. So my question is, why is the dark matter not also expelled by the same processes?
Well, I guess that they are, well, dark matter halo, I assume that, I guess the general picture is the galaxy is inside a dark matter halo. The halo is always there, right?
Okay.
So
the dark matter is not present inside the galaxy itself. So then the question is, how do you get the observed rotation curves?
Oh, well, they are also present. Yeah, they are it's inside the entire halo. That's everywhere, the dark matter. I guess that everything is in the potential of the dark matter halo. So the question is really presumably the baryons fall into the potential, form stars, and then the question is now what happened to them? And one possible ejection is just one of the scenario. Other possibility, as people have suggested, is the potential is so shallow, they probably never really stay there in the first place. So that's another possibility that why there is a lower baryon fraction. That So I guess that you know that whether which picture is correct, that is a open question.
Okay, switching back to the questions in the chat, William Wall is asking about the detector you described for the HAPS mission. That novel quote-unquote detector is the same idea as the bolometers used for detecting far infrared emission. I guess, or William guesses, that it's novel in this particular case of application. So, comment on that?
Yes, the bolometers are, yeah, these are in the far infrared, certainly, in fact, microwave and even gamma ray. So it's applied to really across the electromagnetic spectrum. So but the operating mode is different. In the case of a bolometer mode, and you measure the overall power, for instance, in the microwave background, that experiments, and in this particular case, it's a single photon detector mode. You measure the energy, you detect every photon, you measure basically energy. So the TES itself has been developed around the same time as a microcalorimeter, and so now this is now viewed as a more promising sort of thermometer, if you wish, because before that there are microcalorimeters that are based on doped silicon as thermistors. So, for instance, next year the Japanese satellite will adopt microcalorimeters that are not based on superconducting technologies. Actually, it uses the same kind of microcalorimeters we used on sounding rockets.
Okay, there is another raised hand by a user by the name of Mirabelle. Mirabelle, can you open your microphone? I think you have to unmute yourself and speak. Yeah.
Yes. Well, since the 80s, it has been proposed that high-velocity clouds of atomic hydrogen in the halo of our galaxy require to be stable, to be surrounded by a gas with temperatures of around 10 to the 5 K. And my question is, has been calculated, assuming certain extensions of different extensions of the halo, if that could account for the 50% of baryons in our galaxy, at least?
Yeah, thank you for the question. Yeah, that's indeed that even in the 80s, that through oxygen-6 observations, people studied these that high-velocity clouds and interpreted the oxygen-6 as perhaps from sort of a transition region between hot 10 to the 6 Kelvin to colder phase, this phase. So that gives the indication perhaps they are, that hot halos. In fact, the ISM community have this picture of fountains and chimneys that, basically in the modern term, we refer to as a feedback, stellar feedback. And so this is all recast in I think that in the I guess a galaxy ecosystem. This is very similar idea, I think, to those kind of pictures the ISM community came up with. In terms of closing the baryon budget, I think from a theoretical numerical simulations, I think the general consensus, if you believe these calculations, to account for all the baryons, most of these missing baryons, if you wish, the hot gas, in fact, is probably in the cosmic web instead of around the galaxies. So the hot baryons around the galaxies probably still a smaller fraction of the missing baryons, if the numerical simulations, the results are correct.
Okay, let me read the final question in the chat. And considering it's already Friday morning with you over there in China, let's leave it at that. So Ludwig Klein has the following question. Will you interpret the novel X-ray observations in terms of a Maxwellian distribution and its temperature? And a follow-on, how sure can one be that the hot plasma is described by a Maxwellian rather than having non-thermal features like suprathermal wings? And how much will this uncertainty affect our capability to infer realistic baryon numbers?
Well, the type of hot gas we are looking at is that I think it's a very good question. I don't think it's unlikely it is Maxwellian. In fact, the type of hot gas we are talking about most likely will be much more complicated, involving a range of temperatures, and perhaps that not entirely in equilibrium. So these are all the open questions I think high-resolution spectroscopy is capable of addressing. In fact, once we have this kind of data, we can directly address this kind of questions, but most likely based on calculations and so the type of hot gas I'm describing is going to be multi-phase, complicated.
Okay, with that, we thank you very, very, very much, Wei, for giving us that presentation. And others in the chat, join in applauding and thanking you on this. Have a good night. And for all others, have a good rest of the day. Next week, we will be reconvening at the same hour with a talk on understanding the accelerating expansion of the universe and the Hubble tension. And the talk will be given by Dan Skolnick of Duke University in the United States. So thank you very much, and have
Thank you. Bye-bye.